Do we really understand water? So everybody knows that water has three phases, a solid, liquid, and vapor. But is there more? Water has been studied for centuries. And you'd think that everything there is to know about water would already be known. One day, I happened to meet this guy, Gilbert Ling. He said that the water inside the cell was not like this kind of water. That the water consisted of molecules that were organized, or he called it structured water. This is amazing. If this guy is right, and it looks like he might be right, and then all of biology is wrong.
Welcome back to Decentralized Radio, your one-stop shop for education on how you can take back control of your health and your wealth, and live outside of the centralized systems that are plaguing our society. We're hosting industry experts every Tuesday live, and also releasing podcasts Friday morning.
Dr. Gerald Pollack, PhD researcher, the world expert on water and its effect in our bodies, in our biology. He's the author of many books, including the bestseller, The Fourth Phase of Water. Really a pioneer in this space. And, you know, the theme of decentralized health and research and science, he's encompassing that because this is an area of research that, you know, is not being funded by the NIH. It's not being funded by big pharma. There's no money to be made in water, and it aligns very well with a lot that Dr. Francisco was talking about earlier and getting outside. So without further ado, Dr. Gerald Pollack.
Okay, thank you. Thank you so much. Okay, so I want to talk about the fourth phase of water, and the implications for health and for your health. I guess the first question that arises is, do we really understand water? So everybody knows that water has three phases, a solid, liquid, and vapor. But is there more? So for most people, you know, water has been studied for centuries. And it is a simple molecule. And you'd think that everything there is to know about water would already be known. And in the next slide, I hope to demonstrate to you that that's not the case at all. So for example, clouds. You look up there and you see some clouds, and the clouds are floating. And the clouds consist of water droplets. Water droplets are heavier than air, so you expect that the cloud would descend. But the cloud doesn't descend, at least most of the time. What keeps it up there? Maybe it's something you never thought about, but if you don't know the answer, then you don't know all there is to know about water. Another example, you fill two beakers with water, and you place an electrode in one and an electrode in the other, and you impose a high voltage. And here's what happens. So a bridge forms between the two beakers. And if you move one beaker mechanically away from the other beaker, the bridge persists. And it'll persist indefinitely for a distance up to 3 or 4 centimeters. So tell me, how does it work? What's going on there? And if you don't know the answer, then you don't know all there is to know about water. Something more common than that. If you drop a water droplet on water, the two coalesce instantly. But here's an example where they don't coalesce instantly. It comes from our laboratory. And we've seen droplets floating on the surface of water for up to 30 or 40 seconds before they finally coalesce. So tell me, what's going on? Can you explain it? And if you can't explain it, then you don't understand all there is to know about water. A lizard in Central America. I'm not sure what country it is, but maybe some of you know. Maybe Costa Rica. Anyway, the lizard sits happily on a branch. And when it gets inspired, it will jump from the branch and walk on water. And so because it walks on water, it's colloquially known as the Jesus Christ lizard. And how does it do it? How does it walk on the water? And again, if you don't know the answer, then you don't know all there is to know about water. So this is one of my favorite. So this is a container, a trough filled with water, and it's red. And the reason it's red is because a few drops of red dye are put into the water for reasons that will become obvious in a moment. And here's a magnet, and the magnet is a superconducting magnet, and it sits beyond the container of water. When you turn on the magnet, the Red Sea splits sufficiently that Moses could walk across it. So I saw this demonstration myself in Tokyo, and it's amazing to watch. And it comes with some side effects, like if you're a fisherman, if the water is split, it becomes a little bit hazardous to do your fishing. Anyway, so what I want to demonstrate to you is that you think you know about water, but I just tried to demonstrate to you that you really don't know all there is to know about water. Otherwise, you'd be able to explain all of the slides that I showed. I used to be in another field of molecular mechanism of muscle contraction. And one day I happened to meet this guy, Gilbert Ling. I met at a symposium that was taking place in Hungary. And I came away hugely impressed. Gilbert Ling was a scientist who came from China, and he was chosen the first cohort of Chinese scientists to come to this country. So they looked all over China, and they found a physicist, they found a chemist, and he was the biologist, drawn from all over China. Well, the physicist won a Nobel Prize. The chemist, my Chinese student told me, also won a Nobel Prize. And this guy should have won at least 2 Nobel Prizes for all of his contributions. So what's his main contribution? Well, there are many, but mostly he said that the water inside the cell was not like this kind of water, that the water consisted of molecules that were organized, or he called it structured water. So he said that inside the cells, inside your cells, my cells maybe even, the molecules were kind of lined up and next to one another, forming a kind of crystal. Now, that was anathema to current biophysicists and biochemists who assumed that the water was just like any other water. Well, I was so intrigued that I came home to Seattle, and I don't trust myself because I become enamored of interesting ideas very easily, and I can be deluded into thinking that something is really exciting, but they maybe aren't. So I tried it on my students, and every one of them came back to me and said, this is amazing. If this guy is right, and it looks like he might be right, and then all of biology is wrong. And so naturally, it's easy to be attracted to something like that. But we had no money to study water, so I decided what I'm going to do is write a book. And I wrote this book, Cells, Gels, and the Engines of Life. And the purpose of the book basically was to present Gilbert Ling's ideas in a way that's understandable. So Gilbert had this problem. He'd sit down at the word processor or the typewriter before that. He'd bat out something, and he'd send it to the publisher. And the publisher would publish it. And the word editing, I'm not sure, maybe the word editing is missing from the Chinese language. So his books are formidable to read. And I decided to attempt to make his ideas palatable and understandable to sort of the average scientist or even layman. I'm not sure if I succeeded, but among discerning readers, they'll pick out this book every time. And despite their interest, there's a lot of material in the book, and it takes a while to plow through it. Anyway, finally, I was able to get some money, and we decided to do studies following Gilbert Ling's ideas because they were so interesting and possibly so informative and so important for all of biology. And so we started with his idea, Gilbert Ling's idea. And I must tell you in advance, we more or less confirmed some of his ideas, but we found something beyond what Gilbert Ling was talking about, which I think is really important, and it will become obvious. So the idea, Gilbert Ling's idea inside the cell, is that you have solids inside the cell, and here's a protein, and 70% or so of the solids inside the cell are proteins. And the surfaces of the proteins are mostly charged, hydrophilic. And these little dipoles are meant to represent water molecules. So you can imagine if you've got a negative charge sitting on the protein surface and the water is a dipole, a dipole like a bean with positive charge at one end and minus charge at the other end, that you could imagine that the dipole would stick and another one would stick here and so on, and they would ling up. And conventional thinking among physical chemists is that you might have one or two ordered or structured layers. And Ling was saying, no, it's dozens or hundreds or even thousands. And I'm going to show you examples, if I remember to mention it, of hundreds of thousands of layers where the water is somehow ordered. So this is a massive effect. Anyway, we started with this idea, and if you have a crystal, this is kind of like a crystal. Crystals tend to exclude particles and solutes, otherwise they wouldn't be pure. So if you start with some material that has contaminants, what happens is that contaminants get excluded to get a pure crystal, otherwise not pure. So we started with this idea, and we were lucky we found something very quickly. So this is a chamber, and here's the gel. We chose a gel that was sitting in the chamber, and this is water plus particles. And the particles are actually little spheres commonly used in scientific studies. They're called microspheres. They're about 1 micrometer in diameter. And so we put the gel into the water plus microspheres, and within a few minutes we managed to put it up against the microscope and look. And lo and behold, we found a region where the microspheres seemed to be excluded. And we thought, well, okay, maybe we did find something, but it was even more impressive than that, because if you look at the video, what happens is there's a region here, and the region seems to be growing, and as it's growing, it's pushing out the microspheres. And it's a pretty substantial distance, so it's about 50 micrometers, which is, roughly half the thickness of one of your hairs, maybe not my hairs, but yeah. So it's pretty big by molecular standards. And later, with certain other materials or surfaces, we could find almost 1 millimeter. You don't need a microscope, you could see it with your eye. And so we thought, well, this is pretty interesting, and maybe, we had no evidence, but maybe this is a region where the water is somehow ordered and therefore pushing out these particles. Well, someone said, you keep seeing this thing, you ought to give it a name. And so we called it exclusion zone water because it excludes. And it's convenient because exclusion zone, it's easy to remember. Unfortunately, it doesn't work in Europe because EZ, it's EZ to remember, but we're observing this with many diverse surfaces. Here's another example. This is a polymer. We use this often, and the polymer, it's a sheet, and it's sitting at the bottom of the chamber. We add water and microspheres, and you can see what happens. Same thing. The exclusion zone builds. At this stage, we have no evidence that this is any kind of structured water, although it fits with the idea that it is.
This podcast is brought to you by our lead sponsor, EMR Tech. EMR Tech manufactures high-quality, high-powered red light therapy devices. In my opinion, red and infrared light are two of the biggest nutrient deficiencies in our modern society due to our indoor lifestyles. Red light therapy devices like the ones from EMR Tech can help combat that by providing high-powered red light while being indoors. I personally use mine every morning and every evening. Red and near infrared light is extremely beneficial for energy production in our body because it boosts mitochondrial function and penetrates deep into the cell. It is also extremely beneficial for skin health, eye health, as well as our circadian rhythms. And this is actually pretty much why I bought everyone in my family an EMR Tech red light therapy device for Christmas. EMR Tech panels are low flicker, low EMF, and use targeted wavelengths such as 830 and 630 nanometers, amongst others, to get extremely effective results. For more information, go to emrtech.com and use our code DRadio10 for 10% off your order. That's emrtek.com with our code DRadio, DRADIO 10 to save at checkout.
We did many such studies, and in terms of generality, we found that many, not all, hydrophilic surfaces, that is water-loving surfaces, generate these exclusion zones, and many solutes are excluded. I'd like to say all solutes, But of course, we never studied all solutes. That would be impossible. So it's a very general phenomenon. Next question. Is this water here, is it really different from ordinary bulk water? It seemed that it might be. On the other hand, we had no evidence. We called it easy water, but later we called it fourth phase water because every property that we measured of this kind of water was different from ordinary liquid water. So to give you a hint of it, and please don't let this scare you, I'm not going to go through this entire slide, but evidence that easy water or fourth phase water is physically different from bulk water. And in black is the observation, and in red is the technique that was used. So here are 8 different properties that we and some others studied, and essentially all of it's published. And so I don't want to go through all of it, but I mean, for example, easy is more viscous than ordinary water, and the method we use is falling wall viscometry. But I do want to focus on one particular attribute, which is really important for everything that follows, and that is the exclusion zone has negative charge, typically. And to make that measurement, we used electrodes stuck into the exclusion zone. And we found basically in almost all cases that it's negatively charged. This was a surprise because you started with water. Water is neutral, and somehow it's transformed into negative charge. And the way it works, the way we found that it works, is something like this. So here is the material, like a gel or polymer with a hydrophilic surface. And you start with water, ordinary water molecules here. And you wind up with a negative charge here and positive charge here. This is the exclusion zone, ordered, negatively charged. And you'll notice if the two are apart, basically what's going on is water molecules are being broken and separated into positive and negative. Battery. This is really important because if this exists inside your body, you've got a battery and you've got the option of electrical charge that has the capability of running a lot of systems. And I'll give you an example in a moment. So the way it works is, as I mentioned, you start with all of the molecules here being ordinary liquid water. Liquid water looks like this. And if you have some energy that's able to break the water molecule, you have the positive part here and the negative part here. 2 negatives of oxygen and 1 positive giving you 1 negative. So it turns out that this negatively charged entity, many of these entities gather together to form this exclusion zone. And the positives are kicked out and they accumulate here. So you started with something that's neutral and you wind up with something that's neutral but separated, just like the first step of photosynthesis where charges are separated. And we learned a lot about the structure, and without going through all details, we found that it's something like this. So here's the hydrophilic material, and we started with pure water, liquid water, and we wind up with sheets, 1, 2, 3, 4, each sheet building on the previous sheet. So you get, we see 4 of them, here's a 5th one and a 6th one, and they keep building that way. And as I said, we found up to hundreds of thousands of these sheets. Now, the structure of each sheet, if you were to look in this direction and look at the sheet, looks something like this. It's a honeycomb structure. And you all know honeycomb structures. They're all over throughout nature, so it's not really a surprise that it's a honeycomb structure. But the point is, this is no longer H2O. It can't be H2O because H2O is neutral. And as I mentioned to you, this has negative charge. And if you do the count, you can count the number of negatives and positives. These are oxygens and hydrogens. In a unit cell, you can go and count, and it turns out it's H3O2. So it's not H2O. This 4th phase is H3O2. And it may seem kind of arbitrary to you, but this is negatively charged because if you had H4O2, that would be double this. this is neutral, so H4O2 would also be neutral, but you're missing one positive charge, one of the H's, so you have a net negative charge. And just fairly recently, a paper appeared to confirm this. And I don't want to go into the details of the paper, but I just copied. And basically, in this rather sophisticated study, they found that at interfaces a ratio of hydrogen to oxygen of roughly 1.5 to 1 instead of 2 to 1, which is exactly what we found. And so it was nice to get this kind of confirmation. So what about inside your cells and my cells? Well, the cells are crowded, and practically, and much more crowded than it would appear in this artist's drawing, the artist being my son, who's actually a very talented artist. So the solids are packed really densely, and the amount of water that exists in between the surfaces of the solids is so little, it amounts to a distance equal to roughly 7 or 6 water diameters. So it's really packed, which means that all the water essentially inside the cell is right next to a surface, which means that essentially all the water is easy water. So in your cells, and maybe my cells, your cells are packed with easy water. Your cells are not packed with liquid water, they're packed with easy water. And I like to give the example, of a simple test. If you're brave, you take a razor blade and you cut, right? And if the cells were packed with liquid water, the water would come pouring out like from a breached pipe, but it doesn't come out. Plenty of blood comes out, but the water doesn't come out. And surgeon friends are telling me that the same thing happens if they cut deeply in your abdomen through a muscle, cut right through the muscle, and they don't find water coming out. And so it's not liquid water, it's actually this highly viscous gel-like water, like a raw egg white, which is basically the cytoplasm of a cell. That's the kind of water that exists inside your cells. So many of you know that if you stick an electrode into a cell, that you record a negative electrical potential. And the current view of the reason for this negative electrical potential is very complicated. It has to do with channels and pumps in the cell membrane. And I've written several pieces arguing that that's not the case, and I'm not going to go through the arguments here, but I believe that the reason is much simpler. It's just that your cells are filled with this negatively charged entity, and therefore you stick an electrode in, and you will record negative charge. It's very simple. Now, so next question. Could easy water contain information? For some of you, this may sound awfully weird. For others of you, you know this stuff very well. And so the one way of asking the question whether water or easy water can contain information is to think about a thumb drive and ask, well, how does it store information? And I think many of you know that basically inside your thumb drive is a planar array of transistors, silicon transistors. Each one is located at a grid point, so it's a two-dimensional array. And each one of these transistors has one of two different states, either on or off or 0, 1, or whatever you like. And this distribution of zeros and ones is what stores the information. So the question is there something similar in easy water that could conceivably store information? And the answer is yes. I mentioned to you about the structure of easy water. So each plane consists of oxygens and hydrogens, which are making up this hexagon in a regular array. And it turns out that the oxygens have not 2, but 5 different oxidation state or charge states. So in other words, first you have an array of a two-dimensional array of oxygens and hydrogens, and indeed the oxygens can have 5 different states, not only 2 but 5. So it's got the very, very similar characteristics to your computer memory. Now, so that's one thing about easy water, and then the next thing you might ask, well, is there any evidence that easy water or any kind of water can store information? And I know that some of you know about it. Others will think this is weird. And it all starts, I think, with this guy, Jacques Benveniste. And I'm not going to go through the details, but he had evidence, if a distinguished French scientist, he had evidence that water could store information. And he ran into a problem because the editor of the journal Nature was not very sympathetic to his views. And so an article appeared in Nature saying that this was a trick, a delusion, and this guy lost his career. He had a laboratory of 50 people, and his career went down the hill, and he became a scientific joke. The joke was, you're having trouble remembering stuff? Drink some of Jacques Benveniste water because it contains good memory. So, scientific joke, he died prematurely. Even more famous than him was Masaru Emoto. And he wasn't a scientist. Emoto was a spiritualist. And Emoto did a kind of procedure, I wouldn't say experiment because he was not a scientist. And what he would do, he'd take some water, he'd convey his intention to the water, and then he'd freeze the water. And it turned out that if his intention was positive, I love you, or something like this, the crystals turned out beautiful. And if he said, I hate you, or you fool, or something like this, the crystals were ugly. And some examples here, this was music, a Mozart symphony played to the water. John Lennon, Imagine, Peace, Thank You. And who's from those Spanish? What's the translation of this? You interfere, okay, that's what yeah. And heavy metal music, so anyway, the problem is that many scientists don't take this seriously because what he would do is he would freeze 50 petri dishes of water and he'd choose the one that best illustrated what he wanted to illustrate. On the other hand, his results have been confirmed objectively, but scientists don't take it seriously. Getting taken more seriously was the work of Luc Montagnier, who unfortunately passed a year ago, and he's famous for discovering HIV. So he won a Nobel Prize for that. And he was a friend of Jacques Benveniste, and so when Jacques died, he was so fascinated by the idea of the memory of water that he started doing experiments. And his experiments were highly controversial, yet confirmed by 3 different groups. And I just want to show you what he did because it's kind of amazing. So this summarizes one of his experiments. So he took some DNA, a short strand of DNA, and put it into water or an aqueous buffer. In a sealed container, sealed better than would be indicated by this little cork here, factory sealed. And he put this next to pure water, factory sealed. And they would sit next to each other for a full day. And he would apply some generic kind of energy, like 50 hertz or 60 hertz. And then he'd throw away container A. He'd look at the water. And his hypothesis was that the information about the sequence along the DNA was somehow being conveyed to the water. And that's shown here, some kind of information exchange. He didn't profess knowing exactly the mechanism of the information exchange, but somehow the information was conveyed to the water. So then, in order to check that, to test his hypothesis, he combined this water with all the precursors needed to do the PCR experiment, which you all know now because of COVID, same experiment. And when he analyzed the DNA that was produced, it had the same sequence as the DNA that was sitting next to the water. Yeah, I mean, amazing. So, of course, many scientists and others couldn't believe this result, and I must admit it's hard to believe, but 2 Italian scientists and 1 Chinese scientist published confirmation of this. So, so if we take confirmation as an indication that it's true, it might well be true. And so you can envision in the future that your thumb drive, which is now filled with transistors, could be filled with EZ water, because EZ water is the substrate in which the memory could be housed, filled with EZ water. And it turns out, EZ water, the oxygens and hydrogens are on an atomic scale, not a transistor scale. And we calculated that if it's really true, what Montagnier and many other people reported, that a computer memory could be the size of a pinhead. So it's something for the future that could be really interesting. Anyway, I know that your interest is not in computer memories, and your interest is in people. And healthy people, their cells are filled with EZ water. So all of you look pretty healthy, and so I would say that your cells are absolutely filled with EZ water. So the original question that I was asking is, is EZ water physically distinct from bulk water? And the answer is yes. I had that long list, which actually, if updated, would be even longer. It's a layered honeycomb structure, as best we understand it, and it has information storage capability, and it fills our cells. So it fills your cells.
Artificial blue light from technology is destroying our health. It disrupts melatonin production, sleep quality, and our circadian rhythms, which has been linked to pretty much all chronic disease. It also rewires our dopamine reward system, which makes it addictive by design. That is why I'm so thankful to have found the Daylight computer, the first company in the world making a computer that has a blue light-free screen. They use paper reflective screen technology, so it's blue light free, flicker free, eye strain free, and is easily used outdoors, so you can use technology while getting the benefits of full spectrum sunlight. For more information, you can listen to our recent podcast with the founder of Daylight Computer, Anjan, on his incredibly inspiring story on why he wants to bring technology to the masses that is not detrimental to our health. You can go to buy.daylightcomputer.com/dradio to pre-order the Daylight tablet today and begin using your technology in a fashion that's way more in line with our biology and nature.
Now, the question arises, most of us know that you can't get something for nothing. So your cell phone, if you forget to plug it in overnight, the battery runs down and it's not functional the next morning. So all batteries need charging. Now, I showed you that the EZ structure is basically a battery. It holds energy, but it doesn't come from nothing. Some energy, you can't create energy from nothing. The only way you can get energy is to convert energy from some source to another source. That's one of the principles of physics that I think is okay. And so the question is, well, what charges the water battery? And I must admit, we couldn't figure it out. You can't take this chamber of water and plug it into a receptacle. That doesn't make sense. So I spent a lot of time scratching my head. That's why the hair is kind of thin, trying to figure out. And I couldn't figure it out. And nobody in my lab could figure it out. We couldn't figure. And it was an undergraduate student working in the lab, bored, trying something, and finally he figured it out. Light. It was light that did it. Incident radiant energy, or light. And the way he did it, he was doing an experiment with one of those chambers that I showed you, sitting on the bench. And I don't know, he must have been bored. And there was a lamp that was sitting right next to him. So he took the lamp, shined it on the chamber. And this is actually his discovery, this actual slide. This is obviously a cartoon of the lamp. But basically, he took material, Naphion, a polymer that we use quite frequently. And usually you get an exclusion zone, and the boundary between the exclusion zone and the microsphere region, the boundary is almost always parallel to the surface boundary, which sort of makes sense. But he found that if he illuminated a portion of the region with light from a lamp, you can see what happened to the exclusion zone. It did this. So he calls me in and he says, hey, look at this. And I was amazed. And I was thinking, well, if this guy is right, he's found the source of energy because light builds the exclusion zone. So I told him, turn off the light. He turned off the light and it gradually went down, so it's reversible. Of course, we wanted to know which wavelength of light is most important. So we did studies on this, and we investigated wavelengths from the UV through the visible spectrum, through the infrared. And ultraviolet did nothing to expand the exclusion zone. The visible spectrum did almost nothing, except in the reds that began to show something. And the infrareds, particularly at 3 micrometers, it was amazing. It just, we could, with light from an LED, very weak light, we could build this by a factor of 10. So really powerful effect. So it's infrared energy, which we kind of think about as heat, not exactly the same, but basically, essentially the same. Infrared energy is the most effective. Now, most people think, well, infrared energy, that comes from the sun, and it's true, it comes from the sun. The sun feels warm, and the warmth is essentially equivalent to infrared energy. And roughly half of the sun's energy reaching us is in the infrared region. So we got a lot of infrared energy coming from our friend up there. But in fact, infrared energy is all over the place. And if I were in a room and I were to turn off all the lights, and my camera could record nothing, my cell phone camera, nothing, I couldn't see anything. If I had a camera with an infrared sensor instead of a visible light sensor, I would get a beautiful image of everything, because everything is generating infrared energy. And that's the reason why the military uses it at night. Can't see anything, but if you want to spot the enemy's tanks, you whip out your infrared camera and you can see exactly what's going on. So because infrared energy is all around us, it's from the sun, but also from everything around us, it means the energy required to build EZ water is all over the place. It's abundant, and therefore, if you have a hydrophilic material sitting next to water, you'll always have some EZ water. It doesn't matter whether it's in your body or outside the body, it will happen. If you add more infrared energy, the EZ water will build. And if you remove it, it will go back to the default. And so the energy required, again, you can't get something for nothing. The energy that's required for building this battery, this source of energy for our body, the energy, it comes from photonic energy, from light. EZ buildup is powered by light, which charges the water battery, the plus and minus that are separated, and also orders the water. Because if you start with something that's disordered and you want to create order, you need to put in energy. So that's basically the one part of the story. And so you might be thinking, well, if all you need to do is lie in the sun to build EZ water, because the sun contains so much infrared energy, like going to Hawaii or just lying out here in the sun, a question that should arise from you as well. You get all this energy. Can you capture it? Can you harvest the energy for something useful? And I'm going to show you the answer, and the answer is absolutely. And our cells are doing this all the time, getting a good deal of energy, not necessarily from ATP, from chemical energy, but from electrical energy this way. So it all started, at least in our laboratory, we found that naphthalene occurs not only in sheets, but it occurs in tubes like this. And so I asked one of the undergraduate students, hey, could you take a look at this? Because we wondered whether tubes can also generate exclusion zones. They've got the curvature, and so we weren't sure. And the student was very conscientious, and he started doing the experiments, and he had the answer within a few days. And meanwhile, I was off giving seminars somewhere, and he didn't know what to do next, so he was inventive, and he looked, and he found something that was so interesting. So when I got back, I was sitting in my office. sitting next to a visitor who I can't remember which visitor it was, but I remember it was an important visitor, but the visitor was not so interesting. So the student, I was kind of hoping to do something else, but we went on and on. So the student barges in, and usually the student, I leave my door ajar because I invite the students to come in. So he pushes open the door, and he interrupts, and usually the students are more polite than that. He says, "I found something I got to tell you about." So I was hoping that it would be interesting, because I was getting bored with my visitor. And he said, I looked at this Nafion tube like a straw, and I found that flow is going through the tube without stopping. And I'm thinking, if he's right, this is amazing, because where does the energy come from? Usually, you need a pressure gradient from here to here, like the heart creating pressure to drive through the large vessels. But there's no pressure gradient here. It's just a tube sitting horizontally immersed in the water, and the water is flowing through the tube without stopping. So I was impressed. So it looks something like this. You take a tube, and you first put water inside, make sure there are no air bubbles, and then immerse it in water plus microspheres, because the microspheres help you see what's going on. Take it to the microscope, look at the microscope, and what you see is this. So here's the Nafion exclusion zone. This is a tube, exclusion zone. And the water containing microspheres, so you can track it, is going through. And we had this going for as much as a day and a half without stopping. Essentially, it's indefinite. It keeps going. And someone said, well, maybe this is a kind of strange property of Nafion. Try some other tubes. We couldn't find tubes, but we actually constructed a tube. And we constructed it. This is a polyacrylic acid gel here and here. And first, the gel is liquid, and then it gels. And while it was liquid, about to gel, we stuck a wire in. And we pulled the wire out after it gelled, and it creates a tunnel. So here you can see the tunnel. And then we took this block of gel with a tunnel. We immersed it in water plus microspheres. And within a few minutes, in EZ forms here and here, pushing all the microspheres to the center. And you can see from the video, same result. It flows through. We tried a half dozen different gels, and all of this is published, and we got the same result. And then someone said, well, you think this is all powered by light? Why don't you just add more light and see what happens? So we cranked up the microscope light, and we found that we could get it to go 5 times as fast, and we published that as well. So this is a very general phenomenon. Basically, if you take a hollow tube, put it in water, a hydrophilic tube, the water is running through. So in order for when you have water running through, work is done. And to do work, you need energy. And therefore, the only energy that we could think of that's running this is the infrared energy that's being absorbed. So it's the infrared energy that's being converted into mechanical energy. And basically, the water then is a transducer of light energy into other kinds of energy like mechanical energy. So that raises the question, this is in the laboratory, and the question is, what about this phenomenon? Do you use this phenomenon in some way? So more general question, does human biology use radiant energy, right? I mean, infrared energy. Do you and I use that? Now, Mother Nature, this is the best image I could get of what Mother Nature, at first plants, and obviously step 1 in photosynthesis is light being used to split water into negative and positive. That's the first step. So there is precedent for this, what we found. And, if you imagine that Mother Nature first had her fun with green plants and then decided, maybe a little bit bored, decided to invent animals and humans. She had a choice. One choice is to get rid of this effective mechanism of using light energy, and the other is to keep it. And the question is, did Mother Nature keep this mechanism in some way? And in a way that we could use it. In other words, could we somehow use light as energy? And so I really didn't think too much of it until an event happened. And the idea is, well, we receive infrared energy all the time. Do we make use of it? And one idea is the cardiovascular system. So we got a lot of capillaries that are right near the surface. They receive a lot of infrared energy. Could this infrared energy be exploited in blood flow in capillaries? You wouldn't think so. And I must admit, I didn't think so until I went to Russia. And in Russia, in Moscow, I met my friend Vladimir Voykov, who is basically the head of the biochemistry department at Moscow University. And after we enjoyed some caviar and some vodka, he escorted me to the laboratory. He said, "You got to meet my neighbor." So the neighbor comes in. The neighbor couldn't speak a word of English. And Vladimir is translating effectively. And the guy says, "There's a big problem in the cardiovascular system." I must admit, some element of arrogance. My nose was cutting the clouds, because as a PhD student, I did some simulations of blood flow in arteries and veins, and I thought we had it all worked out. And this guy starts by telling me there's a big problem in the cardiovascular system. So, okay, what's he going to tell me? Well, he had me convinced in 5 minutes that there was a big problem in the cardiovascular system. So what's the problem? Well, the problem is this, and I guess I could illustrate here. So here are the red blood cells. This is what they're supposed to look like. We've all seen pictures of them, and the diameter is 6 or 7 micrometers. But the capillaries are narrower. The small capillaries are 3 or 4 micrometers. So imagine the situation. You got to squeeze these red blood cells through the narrow capillaries, and it requires energy. And you can see in this image, this is some muscle tissue with capillaries, and you can see that the cells are squeezed, right? And in each of these capillaries, this guy's having a really hard time making his way through, and so this is a problem. So the guy is telling me, he said, this requires a lot of energy. So you can imagine you've got a red blood cell, you've got to squeeze it, you've got to squeeze everyone to get through. So the Russians are big on computation, so he calculated, he said, if the heart is responsible uniquely for driving the red blood cells through the capillaries, the heart would need to develop a pressure that's like 1 million times the pressure that it develops. So even if you got high blood pressure, it still doesn't do the job. He says there's got to be something else. And that something else is actually confirmed by another observation, which I'm sure you don't know about. I didn't know about, but my student, Zheng Li, checked. So it turns out there are a half dozen papers at least published in the last half century that demonstrate that if you stop the heart, the blood flow continues. I mean, lower velocity, but it continues, which means there's got to be something else besides the heart that drives the flow, because the heart is stopped, but the flow is continuing. And it's kind of the same conclusion that the Russian guy reached. There's got to be something else to supplement the heart. Otherwise, there's simply not enough energy. It's sort of like, your toilet sometimes will get stuffed, so you got to take the plunger, and it takes you a good deal of energy to clear it up. So anyway, so the idea that occurred to me while I was in this laboratory listening to the Russian guy is we had just found out in the laboratory that if you take a hollow tube, a hydrophilic tube, that blood flow or water flow is driven by radiant energy, by infrared energy. So I'm wondering, is it possible that this very principle is operating in your cardiovascular system and maybe even mine? Might radiant energy help to drive blood flow? So I got my student, Zheng Li, on this, and after he had a successful experiment, he said when I first proposed this idea to him, he thought I was in some kind of drug. He said, this is ridiculous, the idea that there may be something else besides the heart that helps to drive the flow. Anyway, he did the experiment. It was published a few months ago after approximately 12 or 13 rejections, without reviews, most of them. So he took a chick embryo 3 days old, and he lopped off the top of the eggshell, and you can see the cardiovascular system here. He developed an imaging technique to look at some vessels, and here's the result of his experiment. So this is blood flow, velocity, and this is time. So at the beginning of the experiment, what he does is he stops the heart, and you can do that just by injecting potassium chloride. So he stops the heart, and as you can imagine, the blood flow diminishes, but it doesn't go to zero. It goes to some particular value. And then he tests the signature feature of this phenomenon in the laboratory, that you add infrared energy, it goes faster. So he added infrared energy, and you can see it increased by a factor of 3 or so. He stopped infrared energy, and it went down back to the baseline. So from the result of this experiment, it looks like radiant energy does help drive blood flow. And it looks like in your vessels, and as I said, mine too, I suppose, it's not just the heart that's driving your blood flow, it's the vessels themselves. We don't know how much the vessels contribute because there's a technical issue that I don't need to go into, but we don't know whether it's 5% or 95%. But it seems to be an important phenomenon. So basically, yeah, I'm not suggesting that we photosynthesize, but we do use light. And this is one example of how we use light in the cardiovascular system. And I don't have time to go into all of this, but it looks to us that every cell in your body is using this kind of energy, this electrical energy that comes from the buildup of easy water, which in turn comes from the influence of light. Now, so how exactly does that work in your cells? Well, if you go through the steps, so remember, this is crowded. Negative easy water practically fills the cell. It's essentially all interfacial water. Now, you've got a lot of negative charges here, and you know that negative charges repel one another. All they want to do is get away from one another, and that constitutes potential energy, right? When they get away from each other, the potential energy is zero. When they're packed together, their desire to disperse is potential energy. So you've got a lot of potential energy inside your cell, and that potential energy is used to drive protein folding, which is what actually does the work of the cell. In a muscle cell, some kind of folding of proteins gives rise to the contraction, for example. So all this is used, and I actually discuss this in great detail in the book, the cells, gels, and the engines of life. I don't have time to go into it. So the way it works is sort of like this. So you have a protein in its extended fashion. It's surrounded by easy water. And so what happens is that the easy water melts into ordinary water, and the protein folds, right? Now, then it returns back to the original state, and easy water builds up again. On the other hand, if you don't have easy water around it, or don't have enough easy water around it, then the protein is impotent, can't do what it's doing, so your cell is sick, it's non-functional. So this easy water that sits in the cell is absolutely critical for everything that you do. And if you follow the track, so remember, light builds easy water. Easy water has negative charge. Negative charge is potential energy. The potential energy is used for the work or folding of the proteins. And you connect the dots. Light is responsible for work of your cell. And we never think about that. We think it's all chemical energy. But light, through the vehicle of electricity, is conferring energy on our cells. So you ask a question, well, where do we get the energy? And of course, we get energy from food, some more than others, but we get energy from light as well. we don't think about getting energy from light, but we get energy from light. The light is absorbed by the water, builds easy water, and gives us energy. And if you think about the people who don't eat, like the breatharians, this is probably the most famous one, Prahlad Jani, who claimed that he was approached by two angels. He lived in a cave in the jungle somewhere in India. And they told him that he didn't have to eat or drink. It's very humid there. No food. So he went to the Indian government. He said for 65 years, he didn't eat a thing. But he meditated and he prayed. And so the question, of course, is, well, how does he get his energy? And if certainly it's not from food in this case, and apparently it's from light or some kind of electromagnetic energy. And I suppose that if you pray or if you meditate throughout the day, it may be possible that you may absorb more of this than the rest of us. I'm not sure of that, but certainly it's something other than food because he didn't eat. So should all of this matter to you, everything that I've presented? Well, light matters and water matters. And so the question that you might think of to build your health or retain your health is basically what builds easy water in your cells, because you need this easy water in your cells to function properly. And I'm just going to give you a list and briefly go through. Some of them are obvious, some less. The first is water. Drink water, because water is the raw material for building easy water. You drink the water, some gets peed out, other of the water gets converted into easy water, which you absolutely need in your cells. So keep hydrated. We all know that. Excuse me. Another is green juicing. You go to your backyard, you take the freshly grown plants, you squeeze the hell out of them, and what are you squeezing? You're squeezing the water from inside the plant cells, and that water contains lots of easy water. So basically you're taking easy water and you're drinking it directly. And according to the health practitioners I've spoken to, this is hugely effective in promoting health. There are various substances that have been known since Ayurvedic times to be good for health. And we wondered about them. Here are a few: turmeric, coconut water, ghee, turmeric, holy basil. And we tested these, and we found that each one of them, we published that each one builds easy water. And so it's possible that the reason why, say, turmeric is so good for health in diverse areas of your body is that it builds easy water. And you need easy water, and if your cells are deficient of easy water, they won't function as well, and this helps to rebuild it. Sunshine. There's been a lot of talk about sunshine during the presentations and at lunch. In Seattle, we don't see the sunshine so much except in the summer. In the wintertime, it's kind of gray. Sometimes it rains, sometimes it doesn't. But when the sun pops out, everybody's smiling. And, the idea is that, well, maybe it's a psychological effect, and it might be. However, when the sun is shining, there's enormous amounts of infrared energy. Infrared energy can penetrate our skulls. This is known because you can do imaging of the brain from an infrared outside source. It passes through the skull, gets scattered, recollected, and you get an image of the brain. So when that energy is coming from the sun, it reaches our brain, and the brain easy builds up, and we return to our default state, which is not depressed but happy. And so that could be the explanation for sunshine and why it's so effective. And even more so is the sauna, or as the Finns say, the sauna. It's heat. Whether it's warm, whether it's moist or not, it builds easy water. And it's basically infrared energy. So, you walk into the sauna aching and tired, and you come out like $1 million. I've had the experience, and it's infrared energy builds easy water in your cells. And finally, grounding or earthing, which we've seen examples of here, many examples. The earth is negatively charged. I began my career in electrical engineering, and no professor ever told me that the earth was anything but neutral. I found out from a Russian guy who was working in my lab, and he said, he made some remarks about the Earth's electric field. I said, Andre, you're talking about magnetic field. I never heard of an electric field. He said, you never heard of it? Every Russian middle school student knows that the Earth has an electric field, and the Earth is negatively charged. So I went home with a headache, and next morning, a student brings me the Feynman lectures, Richard Feynman, the great Nobel physicist. Volume 2, Chapter 9 reviews all the evidence for the Earth's negative charge. Changed my life because, if the Earth is neutral, it's different from the Earth being negatively charged. And it's fundamentally important. The American school system is deficient. I found out from some Russian friends of mine who went to school at the time I went to school, and they all knew about the negative charge of the Earth. We never heard a word about it. So now it's changed in Russia, and they're, again, not learning about it. I think they need to.
Are you looking to get the benefits of grounding and earthing, but really just can't be barefoot all the time? Yes, you know what I'm talking about, right? Absorbing free electrons from the earth, improving your circadian rhythm and blood flow and vitality and redox. And that is why I'm excited that this show is brought to you by Rizal Shoes. Rizal Shoes are, in my awareness, the only non-sandal grounded shoes. They have slip-ons and they have cool boots as well with laces that are not only grounded via a copper plug, but have leather outsoles made with water buffalo hide. So they're all natural. They are grounded and they're barefoot and minimalist with a wide toe box. This is imperative for foot health, and it's really going to keep you connected in a modern lifestyle setting so you don't have to walk around barefoot all the time. I love them in the winter time. I can wear socks with my slip-ons and not be freezing cold trying to be grounding. You need to check them out, folks. Rizal Shoes, RHIZAL.co. Rizal.co is their website. Use code DRadio at checkout for 10% off and get your shoes. Get grounded, get connected, and improve your health.
So we deal with practical applications because everybody's interested in practical applications. And one practical application is getting energy from water and sunlight. So remember, all of this charge separation is actually built by sunlight or by infrared energy. And so you can imagine if you put one electrode here and one electrode here, you ought to get electrical energy out of it. And indeed, that's what happens. So here are, I think, a dozen or so little chambers, each one containing naphthalene, water, and two electrodes, one in the EZ and one beyond the EZ, connected in either series or parallel. This is a switch. Here's a magnifier with an LED behind. And so if you flip the switch, it lights the LED. So this is just water and light, basically. So the idea is it's possible to get electrical energy from just water and light without depleting the earth of its valuable resources. And I think this is something for the future. It's possible that this could be a source, a practically infinite source of electrical energy for the future. It needs to be checked and tested. It might be a red herring, but at least the principle, proof of principle is there. Another one is getting drinking water from contaminated water. So we have a device that we've actually been working on. It consists of either a naphthalene tube or any tube that's hydrophilic. So you have input flow, and the water coming in could contain all kinds of contaminants, and we use microspheres as representative contaminants to do experiments, but we used real, genuine contaminants too. And so you know what happens by now. An exclusion zone forms here, an exclusion zone forms here, and all the microspheres are then condensed in the center. We developed a so-called differential extractor, which is just a fancy name for two concentric tubes. And the center one collects all the junk and dumps it. And the peripheral one is collected. This is actually easy water, which is essentially devoid of contaminants, and we collect that. And we've been able to achieve as much as 200 to 1 separation in a single pass. And we had a startup company that ran into some difficulties, but we've made considerable progress in upping the throughput. So this has real I think a future, because this is basically it's a filterless filter. There's no physical filter that you need to change or clean or whatever. It's by virtue of the energy from the sun that does the separation and creates the separation that we can see here. And the big prize is salt. If we think of the salt as a contaminant, the idea then is to remove the salt from ocean water and therefore get drinking water from this. We have some preliminary evidence, but this needs to be developed. Now, do I have 5 minutes or not? Yeah. Okay, thank you. Okay, so I want to address something that's come recently, and that's the idea of cancer. And might cancer somehow relate to easy water? This may seem far-fetched, but let me present to you the idea. So basically, the hallmark of cancer is the cells keep dividing. And so the question is, well, what prompts cells to divide? And why do cancer cells just keep dividing? There were studies 50 years ago by a scientist named Clarence Cohn. And what he found out is that the cells that divide, whether cancer cells or other cells that tend to keep dividing, the characteristic is low electrical potential. In other words, small electrical potential for a sustained time. And that was 50 years ago. And I thought there hadn't been too much follow-up, but it turned out in a review article, there was enormous follow-up. It's just that I was outside. So this is a rather complicated slide. It's a review, but let me just explain. Here on this linear axis is the voltage inside the cell in millivolts. So small electrical potential is here, 0, -10, -20, etc. And big magnitude of electrical potential is here. On this side are tumor cells, which keep dividing. On this side are non-tumor cells, which are cells actually ones that keep dividing. They keep proliferating. And so if you look at the cells that keep dividing, whether they're non-tumor cells or tumor cells, this review article shows that the results are uniform, that whenever you have a small magnitude electrical potential, whether it's a tumor cell or a non-tumor cell, keeps dividing. And at the other extreme are non-proliferating cells, and they have large electrical potential, like glia, neurons, skeletal muscle, and they don't divide, or they don't divide very often, and they have a large electrical potential. So what we're really talking about is electrical potential, and in particular, have I repeated? Okay, so if you have a small electrical potential, small magnitude of it, you get cell division. And tumor cells and other cells that just keep dividing, they have small electrical potential. And what that means, according to what I've shown you, is if you have low electrical potential, since the electrical potential is due to EZ water, you don't have enough EZ water. So the cell is pathological because it's missing EZ water. So what you want to do then to reverse the cancer, the therapeutic approach is basically to build EZ water in your cells, to build electrical potential, to go from -10 or 15 or whatever to -60 or 70 or 80. And basically build EZ water to build electrical potential. And those are the same approaches that I detailed. I gave you a half dozen of them as to what you do to build EZ water. And I think the same is true for cancer cells. And this obviously needs to be tested, but basically it's refilling your cells with EZ water And in theory, that should reverse the cancer. It needs to be tested, but it's a very simple hypothesis. It's not a genomic kind of thing, which has been studied for 50 years without a whole lot of success. Okay, so conclusions. I'm sorry to run over time. First conclusion is that water has not 3 phases, but 4 phases. And I put the easy water right here in this position because we found, easy water's structure, this hexagonal structure. Ice also has hexagonal structure, but it's not exactly the same. We found that if you want to freeze water, if you want to go from water to ice, you must pass through the easy phase and then to ice. And if you melt ice, you must pass through the easy phase to get to water. No time to discuss the dynamics, but anyway, that's what we found. And the implications of all this, I think, are rather broad. The most central one is that water is absorbing radiant energy all the time, particularly infrared energy, which it absorbs hugely. And this has many applications. And one application is in biology, and I gave you one example of blood flow, but I also gave you another example indirectly that it's used by every cell in your body. It's not just the cardiovascular system. Another implication is chemistry. We've all sometimes struggled with chemistry books trying to understand the mechanisms. And the mechanisms, when you deal with aqueous solutions, never have I seen anything that involves easy water or infrared energy, charge separation, or any of the things that I presented to you today. So if we're right in at least some of what I presented to you, it means that a lot of the interpretations of chemistry will need to be revised. Weather. So in Seattle, we hear 50% chance of rain tomorrow. Thanks a lot. We don't know, do we bring a raincoat or we not? And part of the reason for this difficulty is that the variables that are used, that are considered, are mostly pressure and temperature. And I've never seen anybody talk about charge. Clouds contain charge. It's not just thunderclouds that contain charge, which is sort of obvious, but all clouds contain charge. And nobody's taken this into account. And my next book, which will be coming out in a few months, I spent 4 chapters out of 19 trying to understand weather from simple basic principles of physics and chemistry. Whether I succeeded is for anybody to judge, but I tried to move from evaporation to principles of cloud formation to hurricanes, typhoons, and what have you, coming out soon. Health. Easy water is critical for health, and you won't find this in any textbooks except books I've written, and I think the evidence for that is, for me, it's fairly clear. If you want to take food, if you want to freeze the food, or if you want to dehydrate the food, it's nice to know something about the principles that underlie it. Practical examples like filtration, desalination, and getting electricity, all of these may be possible from the principles that I've demonstrated to you. And so I end with this book. This is the 4th Phase of Water book. It's become very popular if you check it out on Amazon. And the best part of it, is the diagrams drawn by my son, the artist, who has been busy remodeling his home and doing no artwork for 3.5 years and holding up all my next books. Anyway, thank you for listening. Thank you. Please, do we have time?
Yeah. Thank you so much, Dr. Pollack. All right. We better have some questions, and everyone's shoes better be off after that.
So this is 2024, and I'm reading a textbook just last week, and I'm listening to a lecture, and in the cell they're still talking. Everything is sodium potassium pumps. Okay, so there's not even a talk about this concept at all. What is your thought on, how much, sodium potassium pumps? It doesn't make any sense that we spend more than half of our energy in the cell just maintaining these pumps that is still being taught in all these textbooks. What are your thoughts in terms of how much does that even play? What are your thoughts on sodium potassium pumps and cellular maintaining this negative charge in the cell?
I think it's wrong.
Why in 2024, when this is out there, is it a whole industry based on monetizing the idea of sodium potassium pumps versus this?
Some of that is certainly the pharmaceutical companies. They're interested in finding out, or at least suggesting a mechanism for the action of the various pharmaceuticals they produce, and their favorites are channel blockers and pump inhibitors. So they've got a lot of investment in this, and a lot of investment, for example, in my university, people in the pharmacology department and biochemistry department. A lot of money comes in to study this. So there's a lot of momentum behind it. And if you look at the evidence is clear that this is impossible. And just to
I'm not a scientist, but it doesn't make any sense to me, but it's still being taught.
Well, yeah, but you see, before we did these studies, if you think about it, the inside of the cell is different from the outside. How do you explain it? And so a very simple and logical idea, there must be some gadgetry in the membrane that either pumps some ions in or pumps them out or allows certain ions to go in and go out. But as you pointed out, it was Gilbert Ling who found that just for the sodium pump alone, the cell needed to, I think, 2/3 or half of the amount of energy that could possibly be mustered was used to pump the sodium pump. And now there are more than 1,000 pumps. So, it borders on the ridiculous to think about that. And the same for channels. It turns out, if you think of the cell as being a gel-like entity, the cytoplasm, and if you look at a raw egg white, that's cytoplasm. It's a gel, right? And it turns out that if you stick an electrode into a gel, not the cell, into a gel, you get the same negative electrical potential as you get if you stick it into the cell. The gel has no membrane, no channels, no pumps, no nothing, but it gives you the same result. So, it's kind of illogical to argue that the mechanism is somehow lying in the membrane. It doesn't make any sense. I could give you other examples, but I won't do it. It's bankrupt. The idea doesn't make any sense at all. But it proliferates because one reason is people feel comfortable with ideas that they've learned. They don't like to change. And secondly, the drug companies are making profit on this. Well, that's another issue. Yeah.
I have two questions. First one is, what happens to the extra hydrogen in structured water? Is it evaporated? Does it just sort of go into this nebulous of unstructured water?
We get rid of it. We get rid of it every time we breathe out. Every time we exhale protons. If you exhale into water and put some litmus paper, it'll be low pH. It's low pH, which means we're breathing out protons. So we get rid of them with every breath. We also get rid of them if we sweat, because sweat has low pH. Sometimes urine has low pH as well. So practically everything we do is designed to get rid of those positive charges. As someone pointed out, we're negatively charged entities. And if we're in a region or a zone with lots of negative charge, we feel good. It's actually beneficial. It turns out negative charge builds easy water. If you pass negative charge into ordinary liquid water, it converts to easy water. And so that's why if we're near a waterfall, for example, where there's abundant negative charge, we feel good. If we walk barefoot on the earth, the negative charge seeps into our body, it builds easy water, and we feel good. And because we're negatively charged beings, because the positive charge gets eliminated, we don't like it.
And second question is, have you done any of these experiments in Faraday cages blocking out all EMFs and studying those?
Well, Faraday cages don't necessarily do that. Some believe that Faraday cages do that, but there's a lot of controversy about that. And so, but the answer is no. We haven't done experiments in Faraday cages. But I think it's not so clear that really solves the problem. But thank you for the question. Yep.
When I've gone on Google to see if these experiments replicate, the results aren't great. Like the Montagnier one, it'll be like, oh, it's never been replicated. I'm curious, are there any of these experiments that point to this phenomena that we could do in our kitchen at home?
You can, absolutely. So the simplest experiment with chia seed, you know, chia seed, you put a bunch of chia seeds in water, it forms a gel, and that gel is filled with easy water. But a very simple way is to take one chia seed and expose it to water and put a dye. In my fourth phase book, I suggest which dye to use. And what you see is that you see a chia seed and you find water around it where the dye doesn't penetrate. That's easy water. Outside that region that surrounds the chia, you've got plenty of dye. It just doesn't enter into this region, which is essentially easy water. That's a simple experiment that you could do.
What's the dye and where can you buy it?
I'm sorry, I can't remember which one. There are many of them. There's one that is in the book that I can't remember what page, but if you thumb through it, you'll find it. So you could do that experiment. Also, the kind of experiment that we do on a daily basis is not so difficult to replicate, where you have either a gel or a polymer and put in water with some particles like microspheres, and you could watch the exclusion zone form. It's not complicated to do.
And thank you for the bravery to pursue this for so many years to the point where
I have many enemies. I can assure you, I'm persona non grata in my own department.
But what an act of courage.
Rebellion against what we do. I used to be really popular. I was studying muscle contraction. Nobody cared what my ideas were. I almost became department chair. And then I dipped my toe into water. And I'm widely despised, not only in my department, but throughout much of the university.
Does deuterium concentration impact easy water?
Yeah, well, I hesitate to say because we're only now doing the experiments. So far, again, this is highly preliminary. We haven't done enough experiments with enough controls, but it looks like if you deplete deuterium, EZ grows bigger. And for me, that's not a surprise because the water is then pure. It doesn't have the, quote, contaminant of deuterium in it. And when you have a pure material, you can grow crystals like easy water more easily. So that's what I thought would happen, and it looks like it's happening, but we don't have enough data to say for sure.
Quick question. What are substances that can interfere with making easy water?
Glyphosate is one example. I didn't talk about it, but I mentioned that we tried various substances that have been used since Ayurvedic time, but we wanted to do a control. And so the obvious control was glyphosate. And we did it, and at every concentration, from the smallest to the largest, all it did was diminish the size of easy water. So I've always wanted for a long time to study various poisons. That's one of them. And I'm wondering, this is hypothesis, I'm wondering whether, as a generality, poisons, many of them may operate simply by dehydrating the cell, depleting easy water, because the cell can't work if it doesn't have easy water. But, I'm a little reluctant because a lot of the people doing the experiment are young undergraduate students, and I kind of don't like to expose them to arsenic and such. So, if you want to come and do some experiments.
Do you know what determines the direction of the flow?
That's a good question.
In the tube test?
So we tried to answer that question. And one way we tried to answer is to create tapered tubes. So bigger at one end, smaller at the other. And we found that it always exits the smaller end of the tube. We thought we had the answer until another student tried to make tapered tubes using a different material, and we got the opposite result. So I think I think if you take a tube, I drew it as a right circular cylinder, but the tubes are not like that. It comes in a long tube, and you have to cut the tube. And when you cut the tube, you don't have a right circular cylinder. First of all, you have an oval, and the oval at each end is kind of frayed. And so you have end effects at one end versus the other. You're also doing it near a window. You may get more light coming from one side compared to the other side. And so I think all of these factors may play into what the direction is. Now, if you set the direction, for example, in your cardiovascular system, your heart is pumping, and it kind of sets the direction, then it will follow that direction. And so if the vessels are really contributing, as our results seem to indicate, it will always go in the distal direction from the arteries toward the veins.
Does that mean in your tests that with the same tube and the same set of water, it always went in the same direction, or was it
No, it varies. Yeah. However, once we set the direction, we could take the tube and rotate it, and it always follows the same sense that it had initially with respect to the tube. If that makes sense. I mean, effectively, we don't have a good answer. This is just conjecture as to what's going on.
Could you elaborate on how the hydrogen in easy water has 5 different states?
Well, not so much, but I found that if you read a standard chemistry book, you'll find that oxygen has 5 oxidation states. At first, I was a bit confused. What's an oxidation state? Well, it's basically a charge state. And the charge state that we all know about for oxygen is -2. We call it a valence of -2. But the book will tell you that it's not only -2, but it could be -1, could be 0, could be +1, could be +2. And I, at least I understand it. It's called oxidation state, but it's also called charge state. So it means that the oxygen can have a charge of -2, that's the most common one, -1, 0, +1, +2. So you have all of these variations. Beyond that, I can't tell you.
And this is distinct from the amount of electrons it has?
Yeah, right. Yeah, the electrons versus protons, the net charge. So, based on that, one of the issues that people never talk about, if we think about the periodic table, and we think that every element in the periodic table is neutral, that's an assumption, which might or might not be correct. It might be that elements on the periodic table have net charge. For example, it could be -1 or +1. Could be the reason why the alkali metals bond so readily with the halogens, NaCl, for example, because one is charged and the other has the opposite charge. It's just we need to remind ourselves that all of this is assumption. Nobody's ever proved that elements are neutral. So I'm sorry, I'm just extrapolating on your question. There are so many issues that are based on assumption that has never been proved.
All right, maybe last question from me.
Okay.
I know the answer, but I want everyone to hear
I
it.
might not.
You do know. You told me. What effect does Wi-Fi have on the exclusion zone?
Okay, so so you know what I told you, but you may not. So we did an experiment. There was a young undergraduate in the lab from Korea, and this guy had a personality like none others, and he was great. And he put a router next to the chamber. He turned on the router, and when he turned on the router, we found that there was approximately a 15% diminution in the size of the exclusion zone. And he did many experiments, and he started to write up the paper, and then he disappeared. I couldn't find the guy. I couldn't reach him by telephone. I couldn't reach him by email. He just disappeared, and it was a real surprise for me because the guy had such a charming personality, and he was kind of head of the Korean student organization, and he would sing, and he would do all kinds of things. And he just disappeared. I asked one of his friends if he could find him. Couldn't find him either. So I don't know what happened to the guy, and therefore I'm reluctant to publish the paper without contacting the guy to ask him various questions, because I want to be sure of the result. And if you can't contact the guy who did the actual experiments, it feels a little awkward. So I guess the answer is I don't know, but if we're able to get some money, money is a limiting factor. It's difficult to get money for this kind of work because it runs against mainstream views. If we could get some money, we'd love to repeat the experiments and study in more detail. So many experiments that could be done that we want to get done, but you need the people to do the experiments, and the people cost money. And it's almost impossible to get money from the National Institutes of Health. I think that the word water is not in their vocabulary. For me, it's shocking because, from everything we know, water is absolutely central to everything that goes on. You might expect that because, we're 2/3 water, and that 2/3 is filled with so many water molecules. If you do a molecular count, if you line up all the molecules in the cell and count one by one, more than 99 out of 100 will be water molecules. And to profess, as the textbooks do, that the water doesn't do anything, that 99 out of 100 molecules in your body are useless, they're just there to dissolve the more important molecules of life. You have to question that view. But getting money from NIH or any of the granting organizations to do experiments like this is a real uphill battle. So I spend a good deal of my time trying to seek money to hire the people to do the experiments, but I tell you, it's a real challenge to do that. So.
All right. Thank you so much, Dr. Pollack. Give it up for him one more time.
Thank you. Thank you. Thank you.
All right, we'll take a short break. I think they brought more.